we will explore how Isaac Newton discovered the sine series without using the modern Taylor expansion. We will build the idea step by step using geometry, a differential equation, and a clever series guess. First, let's recall what sine means. We will use the unit circle where the radius is 1. The angle theta is measured from the positive x-axis, and the sine of theta is simply the y-coordinate of the point. We'll label the angle theta and show that the y-coordinate is the sine of theta. Now here is a key idea Newton used. If you study circular motion or a simple pendulum for small angles, the vertical position behaves like simple harmonic motion. This leads to the differential equation. The second derivative of y is negative y. So the sine function is the solution to this equation, with the starting conditions y at 0 equals 0 and y prime at 0 equals 1. These conditions match the geometry. At 0 angle, sine is 0, and its slope is 1. Instead of a Taylor expansion, Newton used a clever series guess. He assumed that the solution can be written as an odd power series, because sine is an odd function. We write y equals a 1x plus a 3x cubed plus a 5x to the fifth, and so on. Now, we differentiate twice. The first derivative is a 1 plus 3, a 3x squared plus 5 a 5x to the fourth, and so on. The second derivative is 6 a 3x plus 20 a 5x cubed plus 42 a 7x to the fifth, and so on. Then we plug into the equation y double prime equals negative y. Now set y double prime equal to negative y. This means the coefficient of every power of x must match. Let's match the coefficient of x first. On the left, we have 6 a 3. On the right, we have negative a 1. So 6 a 3 equals negative a 1. Next, match the coefficient of x cubed. We get 20 a 5 equals negative a 3. Then for x to the fifth, we get 42 a 7 equals negative a 5. We can see the pattern. Each coefficient is determined by the previous one. Now use the starting conditions. We know y at 0 equals 0, which is automatically satisfied by the odd series. We also know y prime at 0 equals 1. From the derivative, y prime at 0 equals a 1. So a 1 equals 1. Now plug a 1 into the coefficient rules. From 6 a 3 equals negative a 1, we get a 3 equals negative 1 over 6. From 20 a 5 equals negative a 3, we get a 5 equals 1 over 120. And from 42 a 7 equals negative a 5, we get a 7 equals negative 1 over 5040. These are exactly the factorial denominators. So Newton's series for sine becomes sine x equals x minus x cubed over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial, and so on. This is exactly the series we know today, but it was obtained by solving the differential equation with a series guess, not by Taylor expansion. Let's see how accurate this series is. We'll graph sine x and the truncated series using 4 terms. Notice how closely they match near 0. That's why Newton's method was so powerful. To summarize, Newton did not need the Taylor formula. He started from a physical equation, guessed a series, and solved for the coefficients step by step. This approach not only gave the sine series, but also showed how differential equations and series fit together beautifully. Thanks for watching.
Don't forget to like this video, share it with your friends, and subscribe to Knowledge Station. Thank you for watching.